All right. So
Great. Our next talk, our next speaker is Sören, and he'll talk about speculative execution and non-interference preservation for compiler transformations. Here, go.
Yes, thank you. So before we talk about SNIP, let's first talk about the S in SNIP, which is speculative execution. And in this part, in this talk, we are interested in speculative. And speculative have this nature that when you take a typical formal semantics, it is architectural. So it talks about program counter, registers, and stack variables, or maybe heap variables. But spectre attacks cannot be visible in here because spectre attacks happen on microarchitecture, right? We leak on side channels, which means like caches, branch predictors, and also we need the microarchitecture to execute, right? We have prediction, branch prediction, so speculative execution, which only happens in the microarchitecture. So let's look at the formal semantics, and we have seen this a little bit already in Santiago's talk earlier, but we will go through it nonetheless. So here's our typical Spectre v1 example, which is a bounce check followed by a load, and then the result of that load is used again as an address. So if we look at an example state at the beginning, which is architectural, right? We would expect that we cannot go into the branch. However, when we do a speculation, especially branch speculation, the CPU might think, okay, we probably will execute this branch. We execute it nonetheless. And what we see immediately is that this load that we execute now speculatively doesn't follow memory safety anymore, right? We have an out-of-bounds access, and it might just happen that this out-of-bounds access aligns with our secret. So we load our secret into A, and then we use A as an address in the second load. And eventually our CPU will realize that it mispredicted and roll back. However, the attack is still going because the CPU has rolled back the architectural state, but we have some microarchitectural state, and we want to capture this leakage approximatively. For example, if we have a conditional, we leak the value that we evaluate the conditional, because we have some, for example, an entry in the branch prediction history table or something that another thread could lead. Similarly, when we load, we will create a cache entry, and so we leak the address. And when we load on the secret, then in the last line, we will be leaking our secret to other threads. So this is one part of the microarchitecture, right? The other part of the microarchitecture is the branch prediction part. And this part, it is the case that when we execute our if condition, we have two options, right? Either we mispredict or we predict correctly. And in order to resolve this, we have this microarchitectural directive part, which we give in the hands of the attacker, right? We assume the attacker can modify the microarchitecture in any way he likes so that he directs our execution and tells us whether we should mispredict or predict correctly. And in this example, for example, we had a mispredicting directive, right? Because we mispredicted our run. Then the second line, we have memory unsafety, right? So we allow the attacker basically to align our memory, right? We give him the chance to say, okay, this memory access will align with the secret rather than with anything else. And as a programmer, we usually don't have in mind how the memory is laid out precisely. Okay, and then if there's an instruction where the microarchitecture doesn't play any role, we just say step. And this completely removes the non-determinism that we get from branch prediction from the microarchitecture. Okay, so in general, okay, sorry, I was wondering whether I have the wrong talk. I'm not sure. I will have to swap if I do, because I think it's the wrong one, actually. Let me check, sorry. No, it's the right one. Okay, sorry. Okay, so in general, our formal semantics that we want to have is that we have a state, then we get a directive from the attacker, right? The directive tells us how to execute our instruction, so we can execute it and derive the following state. But at the same time, we observe some leakage that we have in our microarchitecture. And rather than to have to model the whole microarchitecture in our state, we get to model an approximative semantics for what happens in the microarchitecture. But instead, we can keep our architectural states. Okay. So we have seen how a spectre text works and how we can make it visible in the semantics. There have been mitigations for spectra, and mainly two that are commonly used, which is removing the spectra attack from our code. One is a speculation fence, which just means we cannot speculate beyond this fence, and the other is speculative load hardening. For this talk, you can just imagine of it, if we execute it speculatively, it will just wipe the contents of the register to 0, which means that in the next line, when we use it as an address, we will leak 0 speculatively rather than the secret value. And when we execute it non-speculatively, we will use the usual value that we should use. OK, so this was the S part, right? Spectra and how to mitigate it. Now let's look if we have put mitigations in our code, for example. We would like to know whether, formally give it a guarantee that it is not leaking any secrets. And for that, we have non-interference, right? We have an initial state, and we divide this initial state into a public and a secret part. And whenever we have two states and they coincide on the public part, we just say they are indistinguishable. And non-interference then says, OK, whenever we take any two states that are indistinguishable and let the attacker choose any sequence of directives, we would rather like to have that the leakages are equal, because that means our leakages are completely independent from the secrets, and the attacker cannot derive any information about our secrets. And with that, we can go to SNIP, which is a property of compilers, where we say, OK, we have our source program, and our source program has no spectra attacks, so it satisfies SNI. And then we compile it. We would like to have that it also satisfies SNI, so it has no spectra attacks. And then we say our compiler is SNIP, or our compiler pass is SNIP, if it does this for all programs. Let's look at an example. And the example is register allocation. So we have a source program. Let's check whether it is SNI. It has a bounce check, store of the secret into a buffer, and then later we will access the buffer at int. So there are 3 leakages, and they are all public variables when we look at the top, right? And we do not modify them in our code, so therefore, yes, OK, this is SNI. So register allocation has the job of allocating some registers to registers in a hardware, but some registers might not fit, and therefore we have to spill some registers to the stack, right? For example, in this code, it might just happen that the register allocator decides to spill int, the register, to the stack, and then right before using int, it restores this from the stack. And the question is this SNI? And the answer is no. There is a spectra attack in here, and it happens for the following sequence of directives. So let's go through it. We start with a secret of 42, and at the first line, we relocate into the stack, so we will write stack to 0. We have a misprediction. When we look at the bounce check, again, it is out of bounds, so our misprediction will go to this line, and we will have an out of bounds where the attacker decides now to align it with stack. So precisely the spot where we have relocated int. So when we restore int, we will not load the value 0 that we wanted to leak, but rather we will load a value which is our secret. So we will leak our secret in the next line. So this means that register allocation is not SNIP. And actually, I've reproduced this on all 4 register allocators of LLVM, on code which I derived from libsodium and did slight modifications to it so that I could actually see it happen. OK, with that, we can go to 2 goals that we have in mind for SNIP. Right? The first question is, if I have a compiler pass and I'm sure that it is SNIP, how can I prove it? And the second question is, we have seen register allocation is broken somehow. Can we fix it? So for the first talk, I'm going to talk about this on Popl on Friday. And for the second question, we're going to talk about it today. And we want to talk it in a better way than fixing our register allocated program by just putting mitigations everywhere, right? That is too much performance loss. And we want to reduce the number of mitigations that we have to insert. And this is what we will focus on. So just a bit on the first question, how do we prove it? Because we need to know a little bit about it so that we can argue why our fix is correct. So usually, we have seen this already. We prove compilers correct with simulation relations, which are a relation between target program states and source program states, with this property that if we do some steps in the target program, we must be able to replay them in the source program in a way so that afterwards we can link our states again. And I call this square, I call it the simulation square, and we have an interval, a simulation interval, right? We have one pair of linked state, and then at some point we will see another pair of linked state. This is an interval. And this is a typical way of proving compiler properties. And also we do it here. We do not go into more detail. As I said, we will do this on Friday. But rather, we will try to find such a simulation under our new semantics, which is the directive semantics, for register allocation. And look what fails. So here's our example from just before. The first thing that I was thinking about was, OK, how do I put the simulation intervals? And it's actually quite easy, right? We have the same instruction in source and target side. It's just that our register allocator has inserted some spill code, right, to put registers to the stack and restore them. So let's assume we already did the first interval, and we're at the second interval, and we have this state. And then on the source side, we have the corresponding state from the source execution. And we want to know, OK, what is the simulation relation for register allocation? So what we see immediately in the states is they carry the same values. It's just that int has been relocated to the stack, right? And we see this in the state too. And therefore, we just say, OK, our simulation relation is equality just up to relocation, right? Our values that we have relocated should be relocated. And apart from that, we should have equality. OK, that's the first part. We defined our simulation relation. The second part is, well, let's execute in the target program. And let's execute with a directive where we saw, OK, at some point, we will have a Spectre attack, right? So we execute it, and we arrive at this state where we have overwritten stack. And now we have to replay on the source program. But we have a problem because, I mean, we need a new directive for the source program in order to execute the source program. But our target program has overwritten int, and we cannot reproduce this on the source side, right? So we have to choose just any other directive, for example, out of bounds, and we align with size. So we will overwrite size instead. And then we can do a transition. However, we are not in simulation, right? There's like these two locations which do not coincide. They are not equal up to relocation. And this is a problem, right? We cannot do the inductive steps with our simulation intervals anymore. And in order to fix this, my first approach is, I mean, first, let's just get any simulation relation. And I just say, OK, I redefine my simulation relation. I make it parametric. And I just remember in the simulation relation which parts of the source state are poisoned. I call them poisoned because they have different values, right? So in this case, int and size on the source side are poisoned. And my new simulation relation just says, OK, equal up to relocation, but ignore poisoned locations. OK, so far so good. We can again go ahead and execute our simulation square. We get a first set P1 of poisoned locations. We execute it again for a second set, and so on. So at least we restored our property that we can have a target trace and a source trace and align them together. And this is nice because we know from our example that at some point in the target program we had a secret dependent leak, right? However, when we looked at our simulation intervals for register allocation, we said, OK, it's the same instruction. It's just spill code around it. So if we execute the same instruction on the source side, we have to have some load leakage on the source side as well. And this load leakage must be secret independent because our source program is SNI. And therefore, these values that we leak have to be unequal, right? And in order to be unequal, there's only one possibility. You have to be poisoned. Because our simulation relation tells us, OK, we are equal up to relocations except on poisoned locations. So our slogan is, secret dependent leaks must be poisoned. Or if we frame this differently, if we have no poisoned leaks in our register allocated program, then we already know that our register allocated program is SNI. And with that, we want to try to answer our fix. OK, can we fix the register allocation? The answer is yes. Just take your register allocated program and make it so that it stops leaking poisoned values. Because we know whenever we have a secret dependent leak, it must be a poisoned value. OK, so the rest of the talk, we will talk about how do we stop poisoned leaks. And we need to answer two questions again. First question is, you give me a register allocated program. How should I know that it has poisoned leaks? And the answer to this is, we do a static poison analysis. And the second question is, how do we stop the leak? And we have the answer already, right? We insert a mitigation right before the leak, and that will ensure that this leak will be removed. Let's look at the global fix, right? We start with our source program. We register allocate it with any register allocation algorithm you choose. we do our static Poisson analysis. It will tell us, okay, here's a Poisson leak. Then we will insert a mitigation and replace our register allocated program. Now, it might happen that we have not removed follow-up Poisson leaks, so we might have to do it again. But eventually, we will get that there's no Poisson leaks in there anymore, and then we have a register allocated program, which is SNI. Okay, so now let's look at the static Poisson analysis. Poisson is defined between the target and the source program, right? We had the simulation relation, which told us, okay, in this simulation relation, we have this set of Poisson location. And then we did our simulation square to obtain a simulation interval. And in order to do static analysis, what we do is we create a synchronized product, right? We take the target state and the source state and the set of Poisson locations, and we merge them together in one state. And then one step corresponds to a simulation step, basically. And on this new product, we can do static analysis in order to approximate the locations that are poisoned at every pair of program counters between the source and the target program. Okay, let's do it just as an example on our example. Here are our simulation intervals again, and we start with the initial program counters for each program. And initially, we have an empty Poisson set, right? We start with equal states. Then when we relocate a value, it stays the same value, right? We just have relocated it, so we keep 0 Poisson values. A conditional does not change the state, so we keep 0 Poisson values. Now, the next instruction is interesting because we have seen already, okay, something should happen here. And the question mark is, what do we have to put here statically, right? We have seen earlier how this looks in the dynamic case. We had this out of bounds instruction which aligned on stack, and from that we got that all registers that are on the stack should be poisoned, right? We could, if there's a second register on the stack, we could also poison that. So statically, we have to choose all registers that are currently residing on the stack. And then on the source side, we chose size, and that is why we had to poison size. However, when we do it statically, we could have chosen any variable here, right? And statically, we just choose the variable that we see in our code. This might be subject to some optimization if one wants to implement this. OK, so with that, we can answer that our poisoned positions would be int and buff. And then we have another relocation, right? The poisoned value that is from int in the source code is just relocated to another location, but it stays poisoned. And we are done with our Poisson analysis. Now we can check our leaks. So the first leak happens at a position where there's no Poisson values, and therefore this leak is fine, and we do not have to protect it in the target program. The second leak, the same, right? We have no Poisson values, no need to protect this leak because we know it is secure from the source program. This leak, however, occurs in our set of Poisson values, and therefore we have to mitigate this leak. In order to do so, we just insert a speculative load hardening in front. Now we have to redo our static analysis, and in this case, it will just remove int from the set of Poisson values, and we are allowed to leak it here. And then we have a register allocated program that is actually SNI. OK, to wrap up, we saw formal semantics, which captures directives and leakage in order to approximate microarchitecture. We saw SNI as a property that guarantees us that we have no spectral attacks in our code. We saw SNIP in order to define compilers, which will carry SNI from source to target. We saw that register allocation is actually not SNIP. We saw how to recover a simulation relation, even though this would not guarantee us security yet. We saw that in the simulation relation, we got from that secret-dependent leaks always are poisoned. We found a way to statically approximate where our target program will leak poison values, and then we removed them in order to get a SNIP register location. OK, with that, open to questions.
That's a great talk. The floor is open for questions.
Yeah, thanks for the talk. I'm just wondering whether what you call SNI is just speculative constant time, or is it something else?
Yes, it is, because the leakage model that we choose is the leakage model of speculative constant time.
So why do you call it differently?
Because before I mean, this is a little bit shame on me because I actually didn't know, and there's other definitions which call it similarly, and I think it's not that clear.
Okay.
Now it is clear. I would call it differently now.
But you really mean this for cryptographic constant time code,
Yes.
right?
So thanks for the talk. So I'm curious, like, what other optimizations did you look at or plan to look at apart from the register allocation
Okay,
or
so
transformations? Yeah.
so to answer this, we have seen Santiago's talk. He's targeted the same thing, and we saw quite a few passes already verified on that part. And I myself, in my paper, also did dead code elimination as an example that works, right? But then when I tried to do register allocation, I realized, okay, something's wrong here. And then I did a large fix. And therefore, I have not looked at other than the two.
Thank you.
Other questions?
Did you evaluate for libsodium, like how many speculative load hardening you have to? Do you need to insert to fix the?
I mean, I
problem?
only scout. So the way it happened is that I realized when I tried to prove register allocation correct, it didn't work. And so I was wondering, does it happen in real code? And so I took some libsodium function. I think it was salsa 20. And I compiled it, and I looked at the binary code, and I realized, okay, yes, it is in here, right? So it is actually happening. So I have no idea if you want to do the whole libsodium library, how many times you have to insert something. I cannot tell. Just for the function I looked at, I think it would be just 1 or 2 SLHs.
Okay. So did you do like any kind of evaluation or implementation?
No,
Okay.
it's just theoretical.
Thank you.
So was it implemented in LLVM, or did you?
No, it's just, as I said, I just tried to understand whether this bug actually happens in reality, yes, and then I could reproduce it in LLVM. But I have not implemented
The fix?
the fix in LLVM.
Oh, I see. And
But I would be interested in doing that. So.
okay, so the same principles would apply for any register allocation, right?
Yes, exactly.
And one question is, your analysis is proved, like it can be terminating because the set is finite?
Yes.
Is
I
that
mean,
why you iterate and then you find a fixed point? Like you remove each element from?
The nice part about inserting mitigations is you only have a finite program points where you can insert them, right? And if you insert them everywhere, it will be secure for sure. So you know you terminate at some point. But as we have seen in the example, there is often the case, at least in the example which I drew from libsodium, there's many cases where you don't have to protect the load in the target program. And this is a way to get less mitigations in your code at the end.
And do you know if your approach inserts minimal number, or like do you have a sense of it, or?
Oh, I think this
Or a
is a
gut
hard
feeling.
question to answer really, because I mean, there's like a tool called Blade, which has one approach to reduce the number of mitigations once you know where you have to protect everywhere, right? But it's really hard to say. I wouldn't know of anything that can tell you what the minimal amount is.
Okay, yeah. More questions? Oh, we are way ahead of the time. And well, if none, let's thank the speaker again. Thank you.